Okay. My name is Amanda Silver, and this is
John David Dalton.
He just turned on his mic.
Yep.
We are both on the JavaScript team at Microsoft, so we work on the core JavaScript engine that ships as part of IE 9, 10, and now as part of the Windows Store applications written in HTML and JavaScript. We're really excited to see you all here today. There's never been a build on campus, and so this is definitely a different experience, and it's just really awesome to see everybody, all of the people who are so excited about Microsoft platforms, like actually here. It's just really awesome. So how many of you guys in the room come from a JavaScript background? Okay,
Woo!
So that's
right.
A good number of people. And how many of you guys come from a C, C++, C# background? You could also raise your hand.
Wow.
Okay,
Awesome.
so so the goal of this talk, for the JavaScript people in the room, the goal is to basically give you guys an education on kind of how JavaScript engines have been evolving in the last couple of years, and what you should know so that you can actually write the fastest JavaScript possible against modern engines. And so a lot of the advancements that we'll be talking about happened in Chakra, that ships in IE 10, and in Windows Store applications written in HTML and JavaScript. But they're also applicable for Google Chrome or Firefox or Safari and WebKit browsers as well. Generally, these are just good tips. For those of you in the room who raised their hand that said that they had a C, C#, C++ background, the goal, I think you will also get something out of this talk. I think what you'll find by the end of this talk is that your intuition as a C programmer can actually be applicable when you start to program against JavaScript. That really wasn't the case just a couple of years ago, but now that we're actually doing just-in-time compilation, a lot of your intuition can actually be applicable. So everybody knows that the best apps are fast and fluid, meaning that they are responsive to touch, that they are actually interactive as you start moving through them. And if we look at JavaScript, it originally started as a scripting language for the web. Originally, the performance for JavaScript didn't really matter because you actually didn't have that much JavaScript on your typical website. If you think back about even as little as 5 years ago, most websites were basically static content, and the JavaScript was for minimal AJAX-style interactions. But now, what we're seeing is much richer AJAX applications, as well as just really interactive applications. So if you think about your typical website for like a restaurant that might have static content, that's kind of the one on the left, what really matters there is page load time. And when it comes to JavaScript performance, the way that translates to us is into something that we call script prep time, which basically means that you're looking at how quickly can we actually load the JavaScript, parse it, turn it into something that we can understand, and then interpret it and start executing it. But really, the execution doesn't really matter. For apps that are kind of in the middle, like Gmail or Outlook.com, they might have some certain scenarios in the application that are JavaScript bound, but for the most part, a lot of their interaction is going to be based on DOM interaction, manipulation, maybe even network traffic, other things like that. And for applications that are on the right, that one that you see there is an application called Darkroom that allows you to actually do things like photo editing in the context of your browser. A lot of that is just like any rich client application. Basically, a lot of the basic logic is being written in JavaScript, and therefore, JavaScript is really important, and the execution of JavaScript is really important. Now, if we were to kind of look at the web and ask, what do people think browser performance is about? A lot of people talk about benchmarks. Now, we have a kind of, love-hate relationship with benchmarks. It's useful in a way because it gives us a goal to focus on, and we can actually get the developer team really excited about, we need to do this optimization or that optimization to hit the benchmark. But at the same time, it's not really representative of your typical web application. Benchmarks tend to be very much like a classic compiler benchmark. So how many of you guys have heard of the spec benchmark from the old C days? Just a few, not that many, I see a nod. But basically what these benchmarks are made up of are very loopy operations that tend to do things like math operations and other things like that, but they also tend to be optimized for the browser that they are intending to showcase. And so we really, kind of have this love-hate relationship with them. To us, the thing that we really want to focus on is how we can improve our JavaScript engine to make sure that you guys as developers can deliver the best experience for your users. And so if we think about, again, CNN or some kind of website that might have static content mostly, but maybe some rich media experiences that are in there, the thing that really matters there is most likely not JavaScript performance. It's mostly the performance of the other browser subsystems, but also just loading and network traffic and that kind of thing. For Outlook.com, it, again, would stress more of the JavaScript engine, but it would also tend to stress other browser subsystems like the DOM and so on. If we think about something like Angry Birds or an HTML5-based game or simulation, that actually ends up being very JavaScript heavy. The reason being that the compute for the game is often written in JavaScript, and then you interact with some other kind of object model on top of it, maybe DOM, maybe Canvas, something else, but you're basically writing most of your compute actually in JavaScript. And so when we think about how we should be optimizing JavaScript performance, it's actually very useful to think about these HTML5 games and simulations. So you guys are familiar with Angry Birds. How many of you guys recognize the guy on the right? What's his name again? Num Num, Num Num. Right. Many years ago, I think in 2007, there was another kind of simulation that came on the scene. It was a RIA benchmark called Bubbles, or Bubble Mark. How many of you guys have ever seen that? A few of you. OK. So let's bring that up real quick. Let me just jump to this one, I think. Yes. So Bubble Mark was written by Alexei Gavrilov, I think, in 2007 to kind of test what most of the, how the RIA frameworks kind of compared to each other. And what it did at the time is it basically took a bunch of bubbles and it kind of inserted them into a world. And it had a physics engine where the bubbles could start to interact with each other. Now, at the time, the browser engines were much slower in terms of executing the JavaScript that it took to run this. And so that would have looked much slower. Now, this is kind of a piece of cake for us to run. So what we had to do to actually stress this was to take this demo and expand it so that it was actually something that would stress our JavaScript engine, so we could use that as the basis for this talk. And most of the talk will be demo, and I will get into very deep, like low-level stuff, representation of how we represent types and other things like that in the JavaScript engine. We'll be showing a little bit of assembler code just to give you guys some of that intuition. But for the rest of the talk, I think we'll be focused mostly on this Bubbles demo that we created. Can you bring up Bubbles real quick?
Yeah, let me go ahead and back out of this one.
Yeah.
And then go to Bubbles.
So we created this demo. Can you reload it?
Sure, yeah.
Awesome, thanks. So we created this demo. We actually shipped this on the IE Test Drive site maybe a month, 2 months, 3 months ago maybe now. And we updated it for build so that we can actually do this talk and kind of show you how we optimized this simulation step by step. So let's talk about what this demo actually does. Basically, each one of the little bubbles is a div, and they are all in this little, what we call a bubble tank, that actually has the physics engine for how all of the bubbles interact with each other. And when I talk about a physics engine, what that basically means is that all of the bubbles have properties based on things like what their velocity is, what their size is, what their vector is, other things like that, and kind of what happens when those two start to collide. then they basically have to compute a new value for how they should bounce off of each other. That wasn't quite stressful enough for our JavaScript engine to show you the perf, and so to make it a little bit harder, we also had a Gaussian blur effect, added a Gaussian blur effect so that when the bubbles hit each other, you see that little kind of opacity filter come through. So when they bounce, we apply a Gaussian blur, and that's what you're seeing there. So let's see. So now we can jump back to the slide real quick. Now, what's common to all of these HTML5 games and simulations is that they all basically have an interval at which they paint the animation. So basically, for every frame, they need to do some amount of computation to figure out what the next frame is going to look like. They all do a lot of looping over arrays. So in this case, we're looping over bubbles. If you were to take something like Centipede, that might loop over all of the mushrooms and kind of whether or not the worm is hitting the mushrooms. They also tend to do a lot of math. They might do integer math. They might also do floating point math. They also do a lot of property access, and they basically tend to have objects that do property access. And then they also tend to interact with document object models or other kinds of object models, and then pass arrays in. And so this code that you see here was actually taken from the Bubbles demo. And so we're going to actually kind of take a look at how each one of these steps can be optimized so that you can have the fastest experience for your JavaScript game or animation or simulation. So now let's just jump to the Bubbles overview real quick, just so you guys can actually see the code. So the way that this is constructed, tip number one, obviously, is you always want to load your JavaScript at the end of your file. This obviously allows us to load it last, do the parsing, and kind of getting ready to do the JavaScript execution as the last thing in your app. Now, the demo is basically made up of, again, as I mentioned, the animation frame. It basically does the initialization and kind of creates all of the bubbles. And it also creates all of the stats. It kind of tracks all of the stats, like things like frame rate and other things like that. Now, the bubble tank is basically the thing that contains all of the bubbles in that little world. And then the bubbles know how to do things like bounce off of each other and interact with each other, etc. OK, so now what I want to do is just jump back to the slide real quick. Now, before we go and optimize your application, the first question is JavaScript your bottleneck? Now, we know that JavaScript is our bottleneck in this particular demo because we kind of created it to bring you through this. But the best thing that you need to do is basically recognize that there are other browser subsystems that are involved in your application, everything from networking to HTML to CSS, et cetera. And the best way to figure that out is by sorry, somebody's taking a slide. Maybe I'll go back so you get it. The best way to figure that out is to basically use a good profiler. This profiler image that you see here is taken from a tool that we use at Microsoft that you guys can use as well. We call it XPerf, but I think it's called the Windows Performance Analyzer when we talk about it publicly. And what that allows us to do is to see all of the browser subsystems that are involved in your application, and we can actually tell which ones belong to which browser subsystem. So this little snippet was kind of taken from the browser simulation, the Bubbles simulation, and what you can see is that even for JavaScript, there are actually two things that you kind of need to pay attention to. Number one is the thing in green, which is basically the Chakra engine. You can think about it as the overhead for the JavaScript runtime. It does things like JIT compilation and garbage collection and other things like that, but it's not running your code. It's not executing the native execution of your code. So if you have overhead from Chakra, then that's actually something that you probably want to take a look at. Your goal is really to get the yellow to be as big as it possibly can in your application. So definitely use a good profiler. Talking about profilers, I could have a whole session on that, and in fact, there is a whole session on that later today. Andrew Hall is going to be talking about some new profiling tools that we introduced for HTML and JavaScript in Visual Studio in the last couple of weeks. So definitely attend that talk. That'll be very useful. But another tip is to use other tools. And one such tool allows you to basically create micro benchmarks that allow you to test on other browser subsystems to figure out how it will run. And now I'm not going to steal John David's thunder because he's going to talk about this a little bit more.
All right. So I just need to have it switched over.
Switched over to yours.
Yep.
Sure. There you go.
All right. So I'm going to talk about JSPerf. You can go to it at jsperf.com. Follow it on Twitter at JSPerf. It's a website that allows you to benchmark individual snippets to compare them against each other. Another thing that JSPerf allows you to do is see how those snippets run on different browsers and different devices. So you can crowdsource this basically to other developers, pass the link around, run it on devices, and we'll archive that performance data for you. So you can see, for example, what's the fastest path algorithm for a game that you're designing? Or is it faster to use getters and setters or not use getters and setters in certain situations? Or how to create faster data storage for your application. So I will now take you through just a brief overview of the interface and how to create a good test and talk about some of the do's and don'ts on doing a test. So let's see. So a test is just basically consists of your preparation code, which is where you would put all of your JavaScript, then your setup code, which is where you would define variables, and then let's see if I have something else here. I'll go to one that I'm already editing in process. All right, so you'll see this populated. So this is someone's testing property access for data storage. And they're wanting to see if using an object is faster than using an array or using a typed array in this case. So now they're adding their code and then their test bodies here. So you can give each test a name, put your code you're wanting to test into each section, and then you just say create test. And that gives you something that looks like this. Your tests that you can run. And then it gives you, more importantly, the performance results for each browser environment that you're in. In this case, it's operations per second, so higher is better. The benchmark scores that are sent to browser scope are adjusted for margin of error. So hopefully that will help show a more representative benchmark result for you. Whenever you're computing the result, like say, for example, here after you've run a test, it shows you which test is faster. It also shows you the margin of error in the test, and also will indicate what test is slower and by how much. So that is the gist of JSPerf. I'll talk about what it actually does. We just got done discussing benchmarks and how a lot of them are very micro. In this case, you're wanting to test something that's micro. You're wanting to test individual components of your application. So in this case, it would be appropriate because you're really concerned about the individual pieces. What we do is JSPerf basically is a loop-based benchmark. It calculates the minimum time needed to run for each environment. So for example, older versions of IE, like say IE8, had a different timer resolution. So we know to increase the test time and to use high-res timers where available. So those that are familiar with performance.now, we can use that in modern browsers to get a more accurate time. The test harness that JSPerf is built off of will also run in other environments. So you can run this in Node, Norwal, Ringo. It's tested in very old browsers and very new browsers. It's very robust, to say the least. What it does is you have a setup and a teardown and a test body. And so, for example, the test body here is just this set timeout. So right now we're using a deferred test. In this test body, it actually compiles your setup code, your while loop, and then your test body, and then the teardown. Now that's in a normal non-deferred test. Deferred tests are a little different because that's asynchronous, and we're usually testing like a synchronous operation. But the same general idea is there. There's a setup, a test loop, and a teardown. So,
should we jump to the slide?
Yeah.
Perfect.
All right, cool. So now I'll talk about the do's and don'ts. I'm going to start with the bottom first, just to give you an overview. The preparation is where you would put your script tags or define any environment-specific things, like your HTML that you're needing to do to set up your widget or to set up your interface. We are very lenient in what we allow, and this is a tool for devs, by devs. It's all open source. You can actually go to GitHub, get the source for JSPerf, the entire site, and run a local copy on your own servers. Everything is open source. It's been available for about 2 years, and it's used by framework developers from jQuery, Dojo, MooTools, you name it. Devs go here to get their performance results. So the preparation code allows for your HTML and your setup, or your variables and things that you need to be defined, like HTML. And then your setup allows you to create local variables. So for example, those developing in JavaScript know there's a cost between going from local lookups to global lookups to local variable access. And so you can define your local variables in your setup. And teardown is just the opposite of setup. It allows you to clean up anything that you've done. And basically, it compiles your test body into the test loop and allows you to have unclocked code in the setup, and then starts the timer, runs the test loop, ends the timer. It does this and then takes a sample of runs for you. It automatically runs for 5 seconds, but that's also configurable through the benchmark.js API. And that allows you to reduce the margin of error of each result. So the idea is that when you're benchmarking these snippets, you want to get reproducible results, something that you can point to developers and say, hey, this is what I got, and then they can run it and they'll get the exact same results. And so I worked really hard on creating reproducible results there for you. So the do's and don'ts to creating reproducible results would be things like, don't put your function declarations in your test body. Because those will get hoisted out anyways, and it just adds to confusion from other devs when they're viewing your snippets. Don't include the bare minimum in your test body, because outside factors like DOM access or even just property access on some DOM elements can cause reflows and things like that that will affect the performance of your benchmark and cloud the results. Reset unused variables. Because we're in a loop where a loop-based benchmark, like most benchmarks are, you are vulnerable to things like caching. So for example, Opera caches query selector all results. So if you're wanting to see if it's faster to use get element by ID or query selector all, you're going to go, wow, Opera is really fast with query selector all. But it's because as soon as you do one query, in the next iteration of that test loop, it's cached. So you have to keep in mind that these variables are shared in that test loop, and that if you need something to be reset, you should reset it either in the test loop or in the setup. And that there is caching that is applied to loop-based benchmarks. I mean, that's how benchmark optimizations happen. So be sure to bust things like, for example, string concatenation has caching in it. Eval has caching in it. Query selector all. So you'll be surprised where caching creeps up. If the performance looks too good to be true, chances are something is up, unless it just happens to be some amazing optimization that they did recently. Usually, caching is involved, so you want to make sure that you bust through those caching. Don't introduce randomness into your tests. I've seen a lot of tests throw in math.random, and will randomly select an array, item from an array, or do some kind of behavior. And the whole point of having a reproducible test is that it performs the exact same thing each time. So avoid randomness in your tests. And then don't test asynchronous things synchronously. So a lot of times you'll do like a set timeout or an XHR call or a post message or something that is asynchronous inside your test loop. And that's just a while loop. So it's just going through while, and you're just doing no ops through the whole thing. And so you're not going to measure that. JSPerf has a special option for asynchronous tests, which passes a deferred object that you can then call resolve on to in that cycle. JSPerf also has an FAQ, so if you need help navigating the site or have any questions, the FAQ is there for you. My Twitter handle is @jdalton.
And we'll also both be at the Visual Studio booth after this.
Yes.
So
right.
Great.
Yeah.
So
there's that.
So kind of getting back to the demo. So the next thing that I want to talk about is kind of how to write efficient animation in your application. And the most important thing is not to do useless work. So if we were to take the Bubbles demo and were to profile it, you would actually see that the CPU is pegged to demo this. Now, let me just kind of jump to the actual demo. This is a modified version of the one that we actually published on the web. And this one I modified to kind of show you a certain effect. Now, what you guys see is a frame rate that's going at like 100 and something frames per second, and with 100 bubbles. If I were to lower this to, increase this to 18 or 300 bubbles, then we'll see that the frame rate will start to drop down. And then as we start to really decrease the frame rate, then you'll actually see the visual effect of what happens when there's too much compute going on and it actually impacts the user experience. Now, there's a balance to strike here because, again, if I move it back to even 300 bubbles, maybe 200 bubbles is probably better, it actually looks pretty smooth to you. How many folks think that looks roughly smooth? Probably good enough to kind of publish on your website and say, I shipped a really awesome game, right? And so the trick is, but at the same time, if we go back down to 100, we're going to end up computing over 100 frames per second. And that really doesn't make an impact to the visual eye, right? So that's just not necessary. So how do you avoid that? Well, it used to be that there were lots of tricks that people did using set timeout, where they divided a second by the number of frames that would be painted to the glass per second and all that kind of stuff. But in the last couple of years, we introduced a new API call called request animation frame that actually allows you to modify, to only run as often as the image is going to be painted. So in this demo, we have this animation frame timer that calls our animation frame event handler for every set timeout with 0. Now, this is going to basically be doing as much compute as it possibly can and therefore be basically generating needless frames per second. I can change this to actually use the request animation frame, and I can do the animation frame timer. And instead, I can set it to the request animation frame function. Now, the function that I created actually just does the feature detection for the request animation frame. But it's basically just window.requestAnimationFrame. And then I can just pass in a function that does basically the same thing. It calls demo.onAnimationFrame. And now, if we save this and we rerun the app, well, let me close this one before. Then hopefully what we'll see is that it will basically hover around 60 frames per second because that's the most times that it will actually be painted to the screen. So you're not doing needless animation. So if we go back to the slide, looking at the profile of what happens when we use set interval and set timeout, and we move it to request animation frame or set timeout that's kind of based on the number of frames that will be painted, you'll actually see that the amount of compute for your application goes down significantly. And rather than hearing your fan run and all that kind of stuff, you'll actually end up with a little bit of time in between animations. So another thing to avoid is chattiness with the DOM. If you look at these two different lines of JavaScript code, how many calls to the DOM do you guys see there? 12 total for both lines. Yep. So basically, each one of these lines has 6 different calls to the DOM. Super, super chatty. And the DOM is still basically a host object model. So there's still a major discussion that has to go on between the JavaScript engine and the DOM every time that you make this call. So what we want to do is basically avoid DOM interaction. So again, if we go back into the demo, now let me just close this again. And now if I go into the, find the on number of bubbles change, if we take a look at this, sorry? Oh, I'm sorry. Thank you. Yeah, my frame rate's too low. Good one. This one we might need some technical help on. It doesn't appear to be a problem here. Oh, there we are. Okay, never mind. Okay, so if you look at this, what we're doing here is we're basically calling a query selector into the DOM, and then we're basically getting the value of kind of what's being stored there. And then we're storing that into the number of bubbles, and we're using that variable everywhere after that. Now, this will end up getting passed into a tightly executed loop. And so this looks like it's not being called that many times, but it's actually going to be called like thousands of times per frame. And so obviously what we want to do is cache this. So rather than do that, we want to basically say value equals number of bubbles selector dot value, and just change this to be value, and this to be value, and likewise. The other thing that we want to do is this is still basically getting a string value out of the DOM. And so it's actually useful to do the explicit cast for the compiler, because that tells us that we can expect that this will always be of an integer type. So we want to basically just change this to parse int and save this, and then we can just rerun this. Let's see, wrong folder. Now, what we did in this demo is we actually did the optimization level. So you can actually play with this yourself and see kind of how this impacts the frame rate. I'm going to jump back to the slides real quick. We're running a little bit behind. So definitely check the values from the DOM. That one little line of code in our application actually made for 30% of our time in that frame being computed being devoted to the rendering time of the string conversion and kind of getting the value out of the DOM. So definitely cache and cast. So we go from something like document.getElementById to something like, as I said, this is going to be executed in a tight loop, and without casting, it's going to be passing in a string value. What we want to do is basically parse the int and just pass around the value of the integer so that we can actually do everything super efficiently. All right, so what the impact of this is from a profiler perspective. Now, your code might have been running a good amount before, but now that we're parsing it, we don't actually have to create as many intermediate JavaScript objects to store the values of the string and then pass around all of the references to the DOM functions and all of that. So your GC actually goes down as well. So JavaScript is extraordinarily flexible. You can multiply an int by a string to add to the end of arrays. Objects can create a property and then add another one later. And modern JavaScript engines like to think about your code as if you wrote it as structured and rigorous as possible. So if you can take your structured and rigorous self as a C programmer and kind of bring it into the JavaScript world, you're going to end up writing faster JavaScript code. Now, of course, that comes at the cost of flexibility, so there's a style choice to be made there. But again, we're talking about performance here. So you always kind of need to make that trade-off between do I want it flexible versus do I want it performant. So this just kind of goes through like what the alternative, the more rigorous version of the things on the left would be. So rather than doing multiplication by a number and a string, we actually want to do parseInt to convert it into a number. Rather than having an unsized array, we actually want a fixed-sized array, et cetera, et cetera. So let's talk a minute about the life cycle of your JavaScript code. As I talked earlier, I mentioned that the first phase of the JavaScript engine where we kind of kick in is where the host hands us something that it got off the network, which is a JavaScript file, and it tells us to parse it and figure out what to do with it. Now, one of the things that all of the JavaScript engines have introduced in the last couple of years is JIT compilation. Now, we all do this slightly differently, but we all do it at this point. JIT compilation basically takes the code that you wrote as JavaScript and it converts it into native code. When I say native code, what I mean is basically the equivalent of assembler code that your C or C++ compiler would output as well. So rather than the old interpreted world, it's actually doing JIT. Now, for the Chakra engine in particular, we actually do this JIT compilation on a background thread. So what happens is when your JavaScript code comes in, we parse it, we start to execute it and understand kind of what it's made up of. We create something called an AST, which is an abstract syntax tree that allows us to reason about kind of what's contained in the program. And then we will actually immediately start executing it by running it in our interpreter, which is a lot faster than the interpreter before IE9, but it's still much slower than the result of JIT compilation. At the same time, what we'll do is we'll basically instrument your code to figure out which are the hot loops in your application. And for those loops that are super hot, we will basically pass those off to the background JIT to convert them into native code. And when we're done converting it to native code, then we'll pass it back and we'll basically execute maybe a little bit of native code with a little bit of interpreted code. All right, so the next thing is to create fast objects. Now, most of the code that you write in JavaScript today is object-oriented. And now, I recognize that JavaScript doesn't have a formal object-oriented pattern in it, but we've done a lot of studies on kind of the patterns that people tend to write JavaScript in. And what we found is that people tend to write object-oriented code even though they might not have formal patterns in there. And there are a couple, maybe 10 different types of patterns that people use for writing object-oriented code in JavaScript, and some are faster than others. So the key aspect to object interaction and making that fast is fast property access. And the way that you get fast property access is by avoiding a few no-nos and also making sure that your objects are consistent throughout the lifetime of the object. So fast property access. If we go into the demo, what I want to show you real quick. This one I don't have to type, so it'll hopefully go a little bit faster. But if we go into the bubble, oh, sorry. There we go. Thank you. One of the things that you'll see, let's see, let me just find this. Delete bubble counter. So one of the things, the slow version of the bubble object, actually rather than what happens when a very common pattern in JavaScript that we see a lot, but it's super slow, is people delete a property when they want to reset it to like a default value or to null or to 0 or something like that. That's super slow. It actually causes the JavaScript engine to take it back into a property bag mode. The faster way to do this is to actually keep the property around, but to assign it to 0. So if we go back to the slide again and kind of look at this example, now property bags, the way that they kind of work is that this is the default object that's kind of the catch-all for all objects in JavaScript. And it's like a hash table, essentially. Now, what we can do is we have faster versions of objects. So if you have a certain number of properties, then we can actually use a much faster version of the object that allows us to look up things like vtables. How many of you guys are familiar with the term vtables? So for those of you who aren't, you can kind of think about an internal object representation as though it's like an array, and that all of the properties are slots in the array. And so we can actually look up property values by indexing into the offset that that property is stored at. Now, we can do this for some objects when you basically store things kind of in a rigorous and structured way. But when you do things like delete the property itself like later once it's being used, then we can't do that kind of thing. And so we actually need to fall back to the property bag lookup, and then we're basically, it's like a hash table lookup. In this case, the slow property access was taking up 41% of our CPU time. And that was because of the delete for the bubble bounce counter. Now, if we change this to assigning to 0, then the effect is that more of your code actually ends up running. And so you can actually end up doing a lot more compute in your program. Maybe add something like, I don't know, spaceships or something that will make the app look cooler. So now, objects in JavaScript are also very flexible, like arithmetic in JavaScript. I think I talked a lot about kind of what property bags are, but you can do a ton of different kinds of things. You can add properties on the fly. You can use them as dictionaries. You can enumerate all of the properties in an object to basically kind of loop over all of the properties and do whatever you want to with them. There's a class-like pattern using prototypal inheritance. It's not like something that's super structured. If you want something that's super structured, I would definitely recommend that you check out TypeScript, which is something else that my team has been working on. And I think Anders did a session on maybe soon? Friday? Oh, something like that. Definitely check that out. This will actually help you a lot to make sure that your JavaScript objects are adhering to some kind of structure. But again, it's just property bags. And you can even remove properties in JavaScript. Now, the way that the internal type system works is that when we create an object, we basically create a slot. And for all of the properties that are created, we basically do something that we call type evolution. So you can think about it as we create an initial type that has kind of the basic type. And then as a property is added, we create an evolved type. And anytime we add a property, we basically create yet another object to represent that type. Now, what happens when another object comes along that basically has the same shape? The good news is that it can basically reuse the same bubble object. So that's very good, because it means that we're not creating a lot of internal types that need to be garbage collected and cause stress on the system. So that's generally the best practice. Now, what happens when you introduce something that violates the constraints of the structure that you had created for these objects before? Well, we basically need to create another object. And so if you kind of play fast and loose with JavaScript objects, then the JavaScript engines can't really kind of keep up, and we can't reason about what your intent was, and then we kind of need to back into the property bag approach. Okay. So one of the ways to avoid this is actually to add all of the properties in the constructor. Now, what happens is we can basically use the fast objects for up to a certain number of properties. And actually, you'd be surprised at how low the number of properties is. In I9, I think it was 16. And then for I10, did we make it 30? 30 or 32, something like that. For the other JavaScript engines, it's somewhat similar. But it's basically like a small number of properties. It sounds like a pretty large object, but when you think about inheritance and other things like that, it can actually happen over time. So one of the things that happens is if you add all of the properties in the constructor, then we'll actually give you a bit more leeway, because we know that all of these properties are likely to exist on all of the things that are going to be inherited from it. And therefore, we will actually give you a larger number of properties that we can deal with and optimize for. Don't delete properties. I think we talked about this one. Either set it to undefined or something else. Use identifiers for property names. So it looks like I have a typo here, but if you use strings or something that can't be used as an identifier, then again, we will back into the slow property bag access. And also, don't use getters and setters excessively. Now, this is a fun one, because I think over the next year or so, all of the JavaScript engines are going to optimize this. This was basically something that was introduced in ECMAScript 5, which was ratified last year, so the latest version of the standard. And now that that's been standardized, we can actually do more to inline what's contained in the getters and setters. But we're all still in the process of doing this, and it doesn't exist in IE9 or other browsers below that. So for the browsers in market, you really shouldn't be using getters and setters excessively, because we can't really optimize it. The other thing that we actually see fairly commonly is adding properties conditionally. Yeah. So if you add a property conditionally, again, this is something that will force us to kind of back into the property bag approach, and we can't do optimizations. And also, don't default properties on prototypes. If you have a default value, just basically set the default value. Otherwise, you're going to end up with a lot of intermediate types that, again, will stress our garbage collector and will stress the overall system. Now, I think you guys are pretty familiar with property access in C and C++ and C#. But again, this is basically like that vtable lookup or the array offset kind of lookup that I talked about a minute ago. And it's basically a very small number of assembler instructions. In JavaScript, what we have to do is a lot of assembler instructions to basically look up the property. We have to see where it's defined, and then we have to do the basically execute the result of that. Now, what we can do when we have fast objects is we can actually inline the cache for what that offset is into the object. And so we can go from something that was hundreds of lines into something that's actually a pretty small number of instructions to execute natively. This basically just does the index lookup, and then it kind of reads the value and moves on. All right. So what we're doing here in this case is we're basically looking up the two bubbles. We added them to an array, and now we're iterating over the array. Now, both of the objects have the same type internally. And at first access, what happens is we look up the property, and we actually cache the inline cache. So for the next time, once we get the inline cache, then we don't need to do the slow property lookup. We can basically just use the inline cache directly. So this will just jump to the inline using the inline cache. Now, it's going a little slower than I thought. All right. So what happens when we have mismatched objects is that we will actually end up with much slower property lookup, because we can't use the inline cache. So I've added this b2.c equals red thing, and we had the inline cache. But because the b2.c equals red thing forces you to create yet another object, the inline cache that I had previously created for the previous version of the bubble object, I can't use anymore. And so that causes me to back into the super slow version of it. So you definitely want to use consistent types in your application. All right. So in terms of objects, add all properties in the constructor. don't delete properties, use identifiers for property names, use getters and setters sparingly, avoid conditionally adding properties, and avoid default property values on prototype objects. JavaScript arithmetic. So now, there was a very confounding thing that happened in this application when we were trying to optimize it. We basically saw not a lot of JavaScript execution, the native execution, but a ton of garbage collection. And we didn't quite understand what was going on. Now, what was happening was that it was basically this line that was causing the garbage collection. Now, it's basically based on these two assignments. So let's explain why. JavaScript arithmetic is super permissive. In this case, we can create all these non-numeric types and perform arithmetic on them, right? And JavaScript values are dynamically typed. So what that means is that basically all of the objects actually end up pointing from the stack onto the heap. How many of you guys are familiar with the terms stack and heap? Most everybody. Okay, so I don't need to explain that. Great. So generally, when the JavaScript engine doesn't really know what kind of values are being contained in an object, we store everything on the heap. It's just an object, right? It could be a number that's an integer. It could be a floating point number. Or it could be a string that's text. Or it could be an object that has properties. Or it could be a date or something else, right? But we basically have one stack pointer that points into the heap that kind of stores the value for it. Now, what happens is when you use this super flexibility, we actually can't do any optimizations that would allow us to keep all of those operations on the stack. And so the pseudocode for what the engine generates is something that's kind of like this. It basically gets the type from each of the operands, and then it gets the value from the heap. And then it needs to decide which operation it needs to perform on the values that it was looking up. Is it a concatenation of two strings, or is it an addition of two numbers? Finally, we call the operation, and then the result is boxed back onto the heap. Now, this is a lot of kind of back and forth between the stack and the heap that has to go on, and a lot of helper functions that have to be called. So one of the things that can help with this is if you use integer math. If you actually kind of force everything to be of type integer, then it actually eliminates the need for us to go to the heap for integers, right? And so all of the operations will end up actually happening on the stack. This is goodness, right? So all of the engines do this. With respect to floating point math, obviously, there are times where you need to use floating point math, but use it judiciously. If you can use integer math, definitely use integer math, but definitely use it judiciously when you need to use floating points. And so let's move on to the next one. So one of the things that we've done in the last couple of years, and all of the engines have done this, is I mentioned a bit earlier how we run immediately in interpreted mode, and we actually look at kind of what's happening in your JavaScript code. Now, we do that for a couple of reasons, to find out which functions we need to JIT, but we also do it to find out what kind of values you're actually using in your program. Now, if we find that things tend to be floating point numbers, then we can actually generate what we call type-specialized code that's based on the floating point numbers. So this is the generic machine code, the helper code. We can actually generate type-specialized machine code that's specific to your floating point operations, and then use the Chakra interpreter. Type-specialized functions are super fast, but they actually require consistent argument inputs, and you can't really deviate from this rigor, or else we will basically fall back. So you have to use arguments of consistent types, and don't really change that. In this case, what happens is we assume that based on the initial instrumentation of the first few executions of your program, we assume that this is a floating point number, right? But if you basically fail the assumption, then, so that's super fast. If you break our assumption, then what happens is we bail out. So now bailing out means that we take that native code generation that's very specific to the types and the values that you were using, and we actually back out into the interpreted mode. So that could end up being super slow again, because not only do you need to run in interpreted mode, but you also need to wait for the function to get hot again before we'll even start to look at JITting it, right? And then you're behind the JIT queue, and there's actually a lot of things that can end up happening that can cause this to be super slow. So just be very consistent in terms of when you use floating point numbers. We can make that as fast as native code or C code, but only when you as the programmer use that kind of discipline. So in terms of fast type-specialized arithmetic, be aware of number boxing, avoid unnecessary floating point math, enable type-specializing JIT compilers. Now, JavaScript arrays. So basically, all of these kinds of simulations are very array intensive. They basically generate a lot of floating point numbers, and they start to loop over all of these floating point numbers. One of the things that got introduced, and what that causes, because arrays tend to not be of any specific type, is they cause a lot of intermediate values, a lot of conversions, a lot of objects on the heap, and a lot of the kind of general things that are just not good for JavaScript performance. That obviously causes a lot of garbage collection. So this is a sample snippet of code that was taken from the Bubbles simulation, and we're basically creating an array to show the Gaussian mask that we want to make available on the image, and also the occlusion mask that we want to kind of update, that basically does the filter for that screen. Now, one of the things that was introduced in IE 10 was typed arrays. And all of the major browsers have this now, but you do still need to do feature detection, because most of the browsers on the market don't have typed arrays right now. But what you can do is you can basically specify that the array, all of the values in the array, are going to be of floating point type, and that they're going to have 64 bits. And so the impact of that is obviously that more of your JavaScript code gets executed. So typed arrays and boxing. So I can actually just jump super quickly back to the demo. Now, if I go in here and let me see, I need to go to the bubble tank, and then I want to find the generate Gaussian mask. Find the next one. Here we go. So you see this, this .Gaussian mask equals new array. If I just change this to new float 64 array, and I pass in the mask size, star the mask size, then that immediately allows me to kind of do all of these operations on the stack. I can basically kind of create an array that's of the appropriate size. I don't need to do any heap manipulations at all. So if we go back to these slides, we can talk about this. Definitely take advantage of typed arrays. In terms of from flexibility to performance, obviously you can create arrays that are of an unspecified type. It's definitely better if you can specify what the type is made up of and how many elements are in it. But it's also even better if you can basically specify, like, what the values are going to be in there, what the runtime types are going to be in there. Now, one of the things that we do in the JavaScript engine is we do something called tagging, which allows us to use the first bit to specify what type of value the object is going to be. We call this integer tagging or floating point tagging. And this actually allows us to basically just look at the value and determine from that what type it is. And then we can do lots of things to determine, like, we can make lots of assumptions about what kinds of operations can actually be used on values of that type. Definitely don't use objects as arrays, or vice versa. This is definitely a slow and bad practice. Pre-allocate arrays. What this allows us to do is to create everything on the stack, and we don't need to do things like, in terms of arrays, when you create objects that are arrays of unspecified size, what happens is we'll create a pointer to an object that's on the heap, but then we will also end up with an unspecified size. And when you basically exceed that size of the array, we will create another array. So it ends up becoming like hash tables of lookups and all of this kind of stuff. Super slow. And if you basically specify the size of the array, then we can allocate a fixed size storage space for that. Enumerate arrays efficiently. This kind of goes from the slowest to the fastest. So you can do things like for each, which actually comes with an additional function call that might cause you to capture a closure variable. And that could be even worse from a garbage collection perspective, because you can end up holding on to objects that you didn't intend to. Generally, the direct iteration is the right thing to do. It's also a good practice to cache the length as well. So use arrays efficiently. Don't use objects as arrays and vice versa. Pre-allocate on creation and enumerate efficiently. Use typed arrays to avoid float boxing. So generally what we've gone over so far, use good performance tools. Definitely go to the memory profiling talk later today that's by Andrew Hall. Identify and focus on your bottlenecks. Don't focus on optimizing your JavaScript if it's not the biggest problem in your application. Just work on something else. Like, if it's DOM interaction, work on that. Understand and target modern JavaScript engines. So understand how the JIT gets invoked, what they use, how they store objects internally. This will actually help you a lot more to write fast JavaScript. Create fast objects. Don't do things like deleting. Don't, change your assumptions about what the object contains. Use fast arithmetic by using consistent variables, consistent types in the variables, and cast when appropriate, and use arrays efficiently. So definitely go forth and code it. These are all the build sessions that I thought might be interesting to you guys. The ones that are bold are yet to happen, but the other ones I think you should definitely check out as well. So we will be up here for a few minutes, and then we will be by the Visual Studio booth. Did you want to say something, Jeffrey?
Yeah, can you switch back to the demo?
Sure.
All right, cool. So I just wanted to, in closing, I wanted to show the benefit of good coding practices. So right now, this demo is running at 60 frames a second, and I'm going to now increase the particle size or the particle count to 200, and you'll see the frame rate drop. All right, so now it drops from 60 to 30. Once we apply the optimizations from this talk, you should see the frame rate increase dramatically. So let's see, it's gone back up to close to 60 with 100 more particles on the screen. So that allows you to do more interaction, more physics, more bad guys on the screen, or whatever for your code.
Or things like touch interaction.
Yeah. Show off. Okay, yeah. So you could do things like that too. So these tips can really make a difference in performance, and there's varying levels of degrees of that. So if you're seeing like a poor frame rate, there's probably places for you to investigate in this. So cool, that's it.
Yeah, awesome. Thank you guys for attending.